Hi guys, my research is about the design of two theoretical recovery processes, and they both recover thorium dioxide and several rare earth elements from monzonite ore. These processes are in the study level of design, and mostly they're being analyzed for which process is the most economical option to recover these elements. So here's a little about me. Since y'all can't see me giving this presentation, here's a picture of me. I am a senior in chemical engineering and I just recently got accepted into medical school. I'm from Huntsville, Alabama, and I'm the fourth chemical engineer from my family that graduated from UT. So here's my faculty advisor. This is Dr. Robert Counts. He has helped me and guided me through this past year while studying this topic. Dr. Counts is a professor in the Chemical and Biomolecular Engineering Department, and he currently teaches the senior capstone sequence about green engineering and process economics. So let me give some background about monzonite ore. Monzonite ore is composed of several minerals, including rare earth elements and thorium phosphates. The picture in the top right is a slab of monzonite ore that is normally mined from the ground and then grounded up finely for processing. The table next to the picture is the average mass composition of the elements inside monzonite ore. The thorium content of monzonite varies up to 20%, with North American monzonite ore containing about 5% thorium. We found these average mass percents from other research papers that were able to run tests on monzonite ore to determine their composition. So now a little background about our research topic specifically. Past research has looked at the extraction of rare earth from monzonite ore, but discarded the thorium phosphate compound as waste. Since thorium could be a possible fuel for state-of-the-art nuclear reactors, our research focuses on a way to recover thorium from the monzonite ore. We want to find a process that not only recovers this thorium as a pure product, but also is economically feasible and profitable. So we started by looking at all the current processes that extract rare earth elements from monzonite ore and picked the best pieces of each process. With this, we produced two processes that recovered pure thorium and had the same optimal recovery of rare earth elements. The start point of each process was the same. Both processes started with a 1,000 kilograms per hour flow of monzonite ore, which was then acid leached with sulfuric acid. The product of this acid leaching step is dissolved in water and filtered. By filtering this, the thorium and some impurities precipitated out as solids, while all rare earth elements stayed in the liquid phase. This first step of acid leaching is essential to separating the thorium from rare earth elements. After this step, the two processes start to differ from one another. So the first process we will look at is process A. The monzonite ore and sulfuric acid are flowed into a continuously stirred reactor and then filtered. After this first filtration, the rare earths and thorium are separated into an upper and lower process, respectively. The upper part of the process is where the rare earth elements are converted into sellable products, and the lower process is where thorium is converted to thorium dioxide and purified. The rare earth elements are converted from phosphates to sulfates and then neutralized to oxides to be sold. But to convert from phosphate to sulfates, they must be heated extremely hot and reacted at really high pressure. The lower process is first neutralized and then supercooled, so the silicon sand impurity is removed and pure thorium dioxide is recovered. So now let's look at process B. The monzonite ore and sulfuric acid are flowed into a continuously stirred reactor and then filtered. After this first filtration, the rare earths and thorium are separated into an upper and lower process. So far, this is just like process A. Instead of making the rare earth elements convert to sulfates with high temperature and pressure, an extractor unit is used instead. In this flow sheet, the extractor unit is shown as the cone-shaped piece of equipment with the name C-split. This extractor unit will extract phosphoric acid, and by doing this will remove 90% of the phosphorus from the rare earth elements. By removing the phosphorus from this process, the rare earth elements can convert from phosphate to sulfates without high temperature and pressure. The lower process is exactly the same as process A. So now let's look at the differences side by side. The upper part of both processes is where the biggest difference is. In process A, to convert the rare earths from phosphates to sulfates, they need to be heated really hot and reacted at high pressure. This reactor, named Reactor 2, is designed to support high temperature and high pressure extremes. To heat this process to these extremes, 2 more heat exchangers are needed, and for the same level of purity, another filter is also needed. The major difference in process B is that the process has an extractor system, instead of that high pressure temperature reactor. With this system, only 1 heat exchanger and 3 filters are needed. Overall, this process has less pieces of equipment than process A. Since both processes make the same products and have the same recovery rate, the total revenue is the same for both. Total revenue is found by multiplying the kilograms per hour flow of each product by its sell price. Dollars per hour was converted to dollars per year by multiplying with 8,064, which was the hours in a year that this process would be running. This calculation gives the revenue per year and is used in this chart to show how much each element will make in profit. The 2 biggest money makers were the neodymium and the thorium. Just like total revenue, the raw material cost is also the same for both processes. The graph shows by element how much it will cost per year to pay for the raw materials to run the process. Monzonite ore is the most expensive raw material, but that is also because it is the most abundant. Since the revenue and the raw material costs for each process are basically equivalent, the cost to buy and operate the equipment had to be evaluated to see which process was the better choice. Process A had more equipment than Process B, but even with that factored in, the total equipment cost was still cheaper than Process B. The biggest restriction of Process B is that it requires an extractor system that needs to remove 90% of phosphorus. This system was one of the most expensive pieces of equipment. Equipment cost alone was not enough to determine if one process was better or cheaper than the other, so operating cost was also looked at. Operating cost included steam and ammonia to heat or cool the reactors, electricity to run the agitators, power to run the heat exchangers, and yearly cost of operators to run the equipment. Process A cost almost $3 million more a year to operate, and this was mainly because of the cost to heat and cool the process to these temperature extremes. Process B was significantly cheaper on a yearly basis because it did not have these temperature extremes. Considering that we are extracting radioactive material from this system, we must consider the protection of the workers and the surrounding community from these dangerous materials. Our main concern lies with the thorium and the uranium compounds. For both compounds, proper shielding must be present to limit exposure to any workers. Adequate protection will likely include protective walls, specialized clothing and masks, and ventilation-controlled work areas. Additional protection from thorium dust will include air filters and proper ventilation of the storage locations. This aims to reduce the hazardous exposure to the workers and also the surrounding community and environment. Since thorium constantly undergoes alpha decay into significantly more harmful elements like radon, an off-gas system will be needed for the whole process. This system will operate under partial vacuum and will cause the daughter products of thorium to be trapped onto carbon beds until radon is decayed. The whole process, including the monzonite storage areas, will need this off-gas system in order to be under the OSHA requirements for maximum exposure to radon gas. With all the data, total profit was calculated by taking revenue from products and byproducts and subtracting raw material cost, equipment cost, and operating cost. This is shown in the equation written in orange. Even though Process A had a lower equipment cost, the operating cost was significantly higher than Process B. The cost to heat and cool the process several times due to temperature extremes caused large operating costs. The operating costs are yearly fees, while equipment costs will be paid off within a 5 to 10 year period. So if Process A and B were running for 10 plus years, the difference in profit margin will become significantly greater once the equipment cost is paid off. Process B can also make profit from phosphoric acid being sold as a product. So this, along with a cheaper operating cost, makes Process B the more economically feasible option. Process B will not only be more profitable, but it'll also be a safer process due to not having any temperature extremes or high pressure extremes.